In theory, a crystal is a geometric masterpiece. Its external faces align perfectly, reflecting a flawless, highly ordered atomic structure. But in reality, a crystal growing in nature is subjected to chaos. Unequal access to the crystallizing liquid or interference from adjacent rocks stunts its growth in certain directions, leaving the final object lopsided and irregular. These physical accidents obscure the underlying atomic arrangement. You can examine two quartz crystals that look completely different on the outside, even though their internal atomic lattices are identical. To understand a crystal's true structure, we have to completely ignore the relative sizes of its physical faces. Instead, we have to look exclusively at the fixed angles between them. The first step is to enclose our physical crystal inside an arbitrary sphere. From the exact center, we draw a perpendicular line to one of its flat faces, extending it outward until it intersects the sphere, creating a point called a pole. By repeating this process for every face, we map a constellation of points onto the sphere's surface. Removing the physical crystal and projecting lines leaves a 3D spherical map. This arrangement contains all the angular data required to identify the crystal's symmetry. The problem is practical. You cannot easily measure, publish, or analyze a three-dimensional floating sphere on standard flat paper. We need a method to flatten these points onto a two-dimensional plane without distorting their angular relationships. For that, we use the stereographic projection. To create the projection, we slice through the sphere's equator with a flat circular plane. Take a point in the northern hemisphere and draw a straight line down to the South Pole. Where this line pierces the equatorial plane becomes our 2D projected point. This formal diagram illustrates the mechanic. Capital P on the sphere's surface projects down toward capital S at the South Pole, leaving the lowercase p plotted on the equatorial plane. The equator of the sphere acts as the outer boundary for our flat map. In crystallography, this boundary is called the primitive circle. If we project points in the southern hemisphere down to the South Pole, their lines miss the equatorial plane entirely, heading toward infinity. To keep our map contained, these southern points are drawn upward to the North Pole, plotting intersections safely inside the primitive circle. We have a reliable method to flatten individual points. However, crystal symmetry is defined by intersecting planes, which appear as circles on our sphere. We need to know how these circles behave when flattened. Any plane that passes straight through the center of our crystal intersects the surface of the sphere as a great circle. If we take a vertical great circle, a meridian, and project it downward onto the equatorial plane, the top-down view reveals that it projects perfectly as a straight line cutting directly across the diameter of the primitive circle. But crystal faces are rarely perfectly vertical or horizontal. We have to account for great circles tilted at arbitrary angles. This diagram outlines a tilted great circle. The plane cuts the sphere, intersecting the primitive circle at opposite ends. Projected, the top half becomes a symmetrical 2D arc inside the primitive. The bottom half, projected to the North Pole, forms a corresponding completing arc. This reveals the defining mathematical trait of the stereographic projection. Every circle on the sphere, regardless of its size or tilt, projects onto the 2D plane as a true geometrically perfect circle. Because it preserves the geometry of circles, scientists can measure complex angular distances in 3 dimensions using a standard 2-dimensional drafting compass. Calculating and drawing these circles by hand for every single face on a complex crystal would take an enormous amount of time. To speed up the process, we start with a pre-calculated template, a standard sphere marked with lines of latitude and longitude. We tilt this spherical grid exactly 90 degrees, so its north-south axis lays completely horizontal. These figures track that rotation. The standard geographical orientation is tilted over to its lowest point, establishing an east pole and west pole on the horizontal axis. When this tilted grid is compressed down onto the 2D projection plane all at once, the longitude and latitude lines form a dense network of intersecting arcs. This is the wolf net. The vertical curves are projected great circles, and horizontal curves are projected small circles. Graduated in 2-degree intervals, the wolf net operates as a universal spherical protractor. It allows crystallographers to measure angular distances instantly, bypassing manual geometry. With the wolf net established, we can make a direct comparison between physical space and our abstract map. Take a crystal that is divided by a perfect mirror symmetry plane. On the stereogram, that planar reflection is represented by a single, sweeping great circle arc. If the crystal is pierced by a four-fold rotational axis, its physical shape repeats exactly every 90 degrees. On the 2D map, this symmetry operation forces a projected point to jump along a circular track in strict 90-degree increments until it returns to its origin. 2, 3, or 6-fold symmetry axes follow the exact same logic, shifting the points along small circles at different predictable degree intervals. The WolfNet translates invisible, internal physical rules into immediate visual patterns. By looking at how the dots align, you can categorize the internal structure of the crystal without ever being deceived by its exterior shape. When the measuring grid is removed, the pure geometry of the stereogram remains. It functions specifically because it discards the chaotic, malformed exterior of a physical sample. It condenses dense, three-dimensional angular data into a rigorous two-dimensional framework. This math extends beyond crystallography. Geologists use it to plot the orientation of rock textures, and material scientists use it to analyze how polymers stretch under stress. By understanding a sphere's geometry, we extract the strict, unseen rules governing physical matter, unfolding them entirely onto a flat piece of paper.